Let's start today's topic, Gauss law in electrostatics, statement, proof and application to infinite charged sheet. Let's build this completely from scratch. Part 1 is what is an electric field. Real life picture, rub a balloon on your hair and hold it near small paper bits. The paper jumps towards it without touching. The balloon creates an invisible zone of influence around itself. Any charge placed in that zone feels a push or a pull. That invisible zone of influence is called electric field, defined as force per unit charge. But why is electric field defined as force per unit charged? Wait. Anyway, so we draw fields as field lines, arrows showing which way a positive charge would be pushed. Around a positive charge, lines point outwards in all directions like sun rays from the sun. So electric field, as we all know, the field of influence, the zone of influence. Here is the formula. And field lines जो होती है, we take a positive test charge as arbitrary and then उस पर जो भी impact पड़ता है उसके हिसाब से हम lines बनाते हैं. Around a positive charge, obviously positive charge would be pushed away, so the lines point outwards in all directions. Anyway, so part 2 is what is electric flux. The rain and the hoop picture. Imagine rain falling straight down and you hold a flat hoop in the air. Hoop is like a circular only boundary. Just like अगर हमारा अम्ब्रेला ऊपर से पूरा होलो हो, मतलब उसके आर पार बारिश जा सके बट साइड में बाउंड्री हो, so that's sort of a hoop. So imagine rain falling straight down and you hold a flat hoop in the air. वो एक सर्कुलर प्लास्टिक का आता है जिसे लोग मतलब अपने कमर पे गोल गोल घुमाते हैं. दैट्स होप. एंड होप हेल्ड फ्लैट फेसिंग द रेन कैचेज मैक्सिमम रेन. अगर परपेंडिकुलर आ रही है होप से, सो इट कैचेज द मोस्ट रेन. होप अगर टिल्टेड होगा इट कैचेज लेस रेन. एंड होप अगर ऐसे रखा होगा, hoop held edges on parallel to the rain catches zero rain. So electric flux works exactly like this, except we are counting field lines passing through surface instead of raindrops. The formula for a flat area A in a uniform field E with theta equals angle between E and surface outward normal direction, the direction of the hoop is facing, then this formula works. So flat area A, we have hoop ka area in a uniform electric field. Theta is angle between E and surface says outward normal. So अगर hoop है तो उसका normal उससे angle consider होगा. Here angle parallel है, zero, angle is zero, isn't it? Okay, so surface outward normal, the direction of the hoop is facing. Okay, so here is the formula for a general curved or uniform non-uniform field closed surface. Chop it into tiny pieces dA and add up. For general curved or non-uniform, we take the integral, so a बन जाता है dA. It's still a dot product, and this is integral for closed surface. The circle on integral means this is done over closed surface, fully sealed like a balloon skin, not just an open patch. सो फ्लक्स का भी हुप का एग्जांपल लिया था, वो हमने बस 2D का एक प्लेन इमेजिन किया था. नाउ वी आर सीइंग इन 3D. पूरा एक सरफेस होगा लाइक अ बलून. ओके, सो पार्ट 3 is the core idea of Gauss law. Let's see. Real life picture. Imagine a charge is a sprinkler spraying water outward, sealed inside a balloon of any shape, round, potato shaped, cube shaped. No matter the balloon shape, as long as the sprinkler is fully enclosed, the total water spraying out through the balloon's surface stays the same. It only depends on how much the sprinkler sprays, not the balloon's shape. Gauss law says exactly this for electric charge and flux. The total flux through any closed surface depends only on the charge trapped inside. So, statement of Gauss law, the flux is the charge enclosed upon epsilon naught, which is just a constant. So, in words, the total electric flux through any closed surface called the Gaussian surface equals 1 upon epsilon naught times total charge enclosed within it. Here epsilon naught is a fixed constant permittivity of free space, which is 8.85 times 10 to the power 12 minus 12 SI units. Part 5 proof, starting with a point charge and a sphere. Okay, so setup. Place a point charge Q at the center of an imaginary sphere of radius R, our Gaussian surface. Step 2 is field at the sphere's surface. By Coulomb's law, this electric field equals this, directed radially outwards, because you are taking a probably taking a positive test charge. And Coulomb's law वैसे तो Q1 times Q2 upon 4 pi epsilon, actually R square होता है, Q1 Q2 upon R square, and this is just a constant, but here only 1 is given. Let's see. Let me just cut it, then we can paste it again later. Anyway, so here only Q is given, so this is little confusing to me. Because the charge sits at the exact center, E has the same value everywhere on the surface and always pointing outwards, perpendicular to the sphere's surface at every point. Step 3. Why the flux integral simplifies. Since E radially outward and the sphere's surface normal also radially outward points in the same direction everywhere, the angle is theta equals 0, so cos theta or cos 0 is 1, so E dot dA becomes E dA. Pull E out, it's constant on this surface because कि हमारे पास क्यू भी एक ही है एंड 4 पाई एप्सिलॉन नॉट इज़ कांस्टेंट. अब आर स्क्वायर इज़ आल्सो कांस्टेंट फॉर आर केस क्योंकि हमने एक इमेजिनरी स्फीयर ऑफ रेडियस आर एज्यूम किया है. सो दिस ई इज़ गोइंग टू स्टे सेम, so E is constant, pull it out. Integrating the area only going to give the total surface area of the sphere. So dA is the total surface area of the sphere if we integrate it. So it's only going to be 4 pi r square. Now flux would become E times 4 pi r squared. Substitute E and simplify. Substitute back E from here to here, and 4 pi r square would cancel out. We would be left with Q upon epsilon naught. Key observation, R cancelled completely. The flux doesn't depend on sphere's size at all. So अगर एक पॉइंट चार्ज है उसके अराउंड हम छोटा स्फीयर रखें या बड़ा, फ्लक्स सेम ही रहने वाला है बिकॉज फ्लक्स इज जस्ट द फील्ड लाइंस, राइट. कितना फील्ड लाइंस बाहर जा रहे हैं. सो anyways, so step 7 we have let's generalize state don't derive in exam. Since the result doesn't depend on R, it can be shown using solid angle argument that this holds for closed surface of any shape, not just sphere, and for multiple closed charges the flux adds up. So if we have many charges inside, it would be q1 q2 q3 etc etc, summation of all the q upon epsilon naught. And also ये बस स्फीयर के लिए नहीं है, किसी भी शेप के लिए काम करेगा, but I don't know why. We are going to ask this thing, and charges outside the surface contribute zero net flux, whatever enters one side exits the other. So अगर ये स्फीयर है हमारा तो इसमें से जितना भी चार्जेस जितने भी अंदर है उसकी वजह से फ्लक्स क्रिएट हो रहा है. अगर स्फीयर से बाहर कोई चार्ज है तो उसकी वजह से जो फ्लक्स आता है वो चला भी जाता है बाहर. Okay, so here is our final formula. Part 6 is the application in finite plane sheet of charge. Goal is to find electric field at perpendicular distance r from an infinite flat sheet. So goal is to find E at perpendicular distance r from an infinite flat sheet. Okay, so we have an infinite flat sheet with uniform charge per unit area sigma. तो उस पे uniformly charge distributed हैं and at some distance above that sheet we are trying to find out E. Okay, so symmetry argument, since the sheet is infinite and uniformly charged, E must point perpendicular to the sheet, straight away from it on both sides with equal magnitude at equal distances. With equal magnitude. What? Wait. With equal magnitude at equal distances from the sheet on either side. Okay, so what they are saying is कि क्योंकि शीट इनफाइनाइट है और यूनिफॉर्मली चार्ज्ड है, क्योंकि उस पर पूरे पे यूनिफॉर्मली चार्ज्ड है, सो द फील्ड इज़ गोइंग टू पॉइंट आउटवर्ड्स लाइक दिस and a particular distance पे its intensity is going to stay same, magnitude is going to stay same at equal distances. Okay, so step 2 is choose the Gaussian surface, a cylinder. Pick a cylinder that pierces through the sheet symmetrically, its axis perpendicular to the sheet with its flat ends, each area A sitting at distance r on either side. So here is the symmetric uniformly charged plane, and here is the cylinder. So this is how we are going to put it together at r distance. Its circular ends are at r distance. Why this shape? Because E is either exactly parallel or exactly perpendicular to each part of this surface, making flux easy to calculate. Same reason we choose a sphere for the point charge. Flux through the curved side. On the curved side, E perpendicular to the sheet, so E is perpendicular to the sheet, runs parallel to the surface, so it never pokes through. Okay, so क्योंकि वो perpendicular है, मतलब उसके साथ साथ जा रहा है and parallel to the surface, so उसके थ्रू कोई भी थोड़ा सा भी इलेक्ट्रिक फील्ड नहीं जाती, so it doesn't poke through. Angle between electric field and the curved surface normal is 90 degree. So surface का normal consider करेंगे with the electric field, it's going to be 90 degree. So cos 90 is 0, so the flux is going to be 0, and we can see it intuitively as well. Step 4 is flux through the flat ends. At each flat end, E is exactly perpendicular to the sheet. Now flat ends पे E is parallel to the normal, and at each flat end E is exactly perpendicular to the sheet, and parallel to the normal, matching the flat ends normal direction. Angle is 0, cos 0 is 1, so the flux is EA. We have two ends. By the way, इसमें क्वेश्चन में तो बस एक ही बार पूछा था ना, find E at perpendicular distance r. Find E at perpendicular distance r from an infinite flat sheet with uniform. तो बस एक ही साइड का पूछा था ना. Why are they considering 2EA? Anyways, so electric flux at distance r, दोनों side would be EA and EA, so 2EA. Enclosed charge, the charge enclosed is the piece of sheet inside the pillbox, cross sectional area A. So enclosed charge would be sigma charge density times area. So जितना भी area के according charge है distributed है and जितना हमारे पास area available है, so charged and closed. So apply the Gauss law. E dot dA closed integral is going to be Q enclosed upon epsilon naught. Now this Q enclosed is sigma A epsilon naught, and this turned out to be 2EA. Cancel A. We get electric field as sigma upon 2 epsilon naught. Note this is independent of R. The field strength is same no matter how far you are. Wait. So abhi I have two confusions, right? I actually forgot. थोड़ा सा. तभी मुझे पहले ही लिख लेना चाहिए था. यस, कि एक तो ये सॉलिड एंगल आर्ग्यूमेंट कैसे काम करेगा, एंड द सेकेंड इज 2EA कैसे आया, क्यों आया. एनीवेज, नॉट दिस इज इंडिपेंडेंट ऑफ आर. वी गोइंग टू आस्क द 4 डाउट्स अभी. इसके बाद नॉट दैट दिस इज इंडिपेंडेंट ऑफ आर. आर इसमें नहीं है. सो द फील्ड स्ट्रेंथ इज सेम नो मैटर हाउ फार यू आर फ्रॉम एन इनफाइनाइट शीट. Worth mentioning if the question asks for significance. Okay, so flux is going to remain same or field is going to remain same. But ये तो electric field है ना. The field strength is same. How is it the field strength same? मतलब strength infinite sheet के पास ज़्यादा नहीं होगी क्या? But anyways, this formula implies that it's going to stay same no matter how far you are from infinite sheet. Let's ask doubts. Solid angle argument works by take 2A and we needed to find it at just 1 hour distance. ये शायद मुझे स्टूपिड लग रहा है क्योंकि शायद मुझे समझ आ गया. बट एनीवेज, आई एम गोइंग टू स्टिल आस्क. आई विल स्टिल आस्क टू कंफर्म. एंड वन मोर थिंग वाज व्हाट. और कुछ भी था ना, एक चीज़ और थी शायद. Maybe this independent R. This is independent of R. Let's see. I'm a little tired already. Answering your 4 questions, they are exactly whatever. Let's take. Why is electric field defined as force per unit charge? The problem this definition solves. Imagine you want to describe how strong the electric influence is at some point in space. Say 1 meter from the charged ball. If you say a charge P placed there feels a force of 5 newtons, that's incomplete information because the force depends on how much charge you place there. Place charge 1 coulomb there, maybe it feels 5 newton. Place a charge 2 coulomb, it will feel 10 newton, twice the charge, twice the force from coulombs low. Place a charge of 0.5 coulomb, it feels 2.5 newtons. The force keeps changing depending on what test charge you bring, but something about that point in space should be fixed. Fair property, independent of what charge you happen to test it with. Real life picture. Think of a wind speed. If you want to describe how windy it is at a spot, you don't say a sailboat there feels 200 newton of push because that depends on the sailboat's size and size. Instead, you describe wind speed, a property of air itself, and then force on any specific object equals wind speed times that object's exposed area roughly. Okay, so electric field is that fixed property of the point in space obtained precisely by dividing out the Test charge is own size, dividing out the test charge's own size. So force upon this Q naught. I still did not understand why. This way, E describes the field itself, a property of source charge and location completely depends on whatever what a property of source charge and location completely depends on whatever test charge you use to probe it. Double the test charge, double the force, but E stays the same. That's the whole point of the definition. So the speed was, sailboat ki speed was wind speed times object's area exposed. Force equals, right? So force equals wind speed times charge placed in the field. So अच्छा एक्चुअली जिस तरीके से लिखा हुआ है ना डेट इज़ क्रिएटिंग इन्फ्यूजन क्योंकि अगर ये क्यू नॉट उधर लिखा होता तो इट वुड बी easier to understand intuitively. Anyways, I got it. Like this is force times wind speed की जगह इलेक्ट्रिक फील्ड एंड इलेक्ट्रिक फील्ड कितना उस पर फोर्स लगाएगी डेट डिपेंड्स ऑन कि सामने कितना चार्ज है. सो क्यू नॉट, we are taking a test charge anyway. So question 2 is Coulomb's law. Why q1 q why Coulomb's law has q1 q2? Why does step 2 only have q? Excellent catch. This connects directly to question 1. Coulomb's law: the force between two charges q1 q2 separated by distance is this is complete Coulomb's law. Now in our Gauss law derivation we have one source charge q, the one we are enclosing with our Gaussian surface, and we are asking what is the electric field created by this charge q at distance r away. To get the field, we imagine placing small test charge q naught at that point. Calculate the force on it using Coulomb's law, then divide by q naught. For question 1 to get the field. What? So here is the Coulomb's law. We have q and q naught. फिर से एक मिनट. Now in our Gauss laws derivation we have one source charge q that we are enclosing with our Gaussian sphere, and we are asking what is the electric field created by charge q at distance r. To get field, we imagine placing a small test charge q naught at that point. Which point? To get the field, we imagine placing small test charge q naught at that point. Calculate force on it using Coulomb's law, then divide q naught to get electric field. Anyway, so we have q sphere के surface पे, I guess we are placing q naught. So this is going to be the total force. Now electric field is force upon q naught. So electric field is going to turn out to become this. Okay, now it's super clear. The test charge is q naught cancels out because E is defined specifically to be independent of the test charge. Because E is defined specifically to be independent of the test charge, what's left over is just source charge q, which is exactly the q you see in step 2 formula. Okay, question 3. How does the solid angle argument work? Let's slow this down even more than before since it's generally one of the trickiest ideas here. The setup. We have a charge q, and instead of a nice sphere around it, imagine lumpy irregular closed surface like a potato shaped surrounding it. What is a cone of field lines? Imagine the charge q spraying field lines outward in all direction like a sprinkler. Now mentally group a narrow bundle of these lines into a thin cone spreading out from the charge. Okay, so real life picture, like a narrow flashlight beam, a cone of light spreading out from the bulb. This thin cone, as it spreads outwards, will eventually poke through a lumpy surface somewhere, creating a small patch there. What determines how much flux passes through that patch? Flux through that small patch is electric field times patch area times cos theta. Angle between field and patch normal. Okay, so here's the key physics fact. As this cone travels farther from the charge, two things happen simultaneously. The field gets weaker by Coulomb's law because it is inversely proportional to r square. So if the patch is twice as far away, the field there is four times weaker, the patch gets bigger. A cone that started narrow at the charge spreads out to cover a large area. So farther out it travels, specifically geometrically, the cross sectional area of the cone fixed angular width covers at distance r grows by r square. So if the patch is twice as far away, the patch of surface it hits is four times bigger. So if we have a small sphere and यहाँ से we are taking a cone, it is a 3D cone, not just an angle. So पहले just like even in 2D यहाँ पे कम distance cover करता है angle यहाँ पे ज़्यादा. So this is what they are talking about here. These two effects are opposite and exactly cancel. What shrinks as 1 by r square due to distance from the electric field, and the other grows by r square. The area it grows with r square. Flux through the patch is E times area, which is this. So it is going to stay constant क्योंकि cancel out होता रहेगा. Electric field इस पर dependent है, area इस पर. So the flux overall is going to stay constant. Real life picture: shine a flashlight cone at a wall 1 meter away, you get a small bright circle of light. Move the wall 2 meters away, the circle of light is bigger but dimmer. Same total light energy spreads over more area. The total light energy passing through the now bigger circle stays the same either way. Only the concentration or the brightness changes, not the total amount. This means no matter how far or how tilted the patch of our lumpy surface is, as long as it's hit by a cone of certain angular width d omega, I guess this is omega, the flux through it is always the same fixed amount depending only on d omega, not on the distance or tilt. Got it. So imagining a flashlight, अगर flashlight से light जा रही है तो light उतनी ही रहने वाली है. इवन इफ वॉल यहाँ पर है या यहाँ पर है, इट्स गोइंग टू स्टे सेम. उसका सरफेस एरिया बढ़ जाएगा. यहाँ पे ब्राइट दिखेगी, यहाँ पे थोड़ी डिम दिखेगी. एंड अगर वॉल मतलब सरफेस इज़ नॉट लाइक स्ट्रेट, स्टिल द लाइट तो उतनी सेम ही रहने वाली है ना, तो उसके सरफेस से कुछ फ़र्क नहीं पड़ रहा है. ओके, सो स्टेप सी, adding up all the cones. Since every tiny cone contributes flux depending only on its angular width d omega and not on the surface distance shape, adding up the flux over the entire lumpy surface is the same as adding up all the angular widths. So this is 3D angle which is making a cone. And here the crucial geometric fact: if you group all possible directions spreading out from a point covering every direction in 3D space, a complete sphere of direction, they always add up to same fixed total called the total solid angle. So जैसे एक सर्कल का complete 360 डिग्री होता है, so here 3D में the complete 3D angle for a sphere is 4 pi radian. So this 4 pi is just geometric fact about 3D space. The same way all directions around a point in 2D always add up to 360 or 2 pi radians, regardless of what shape you draw around that point. Since a closed surface, since a closed surface by definition surrounds the charge completely, every direction from the charge eventually hits the surface somewhere. Summing up all the tiny cones contributions gives the same total flux as it did for the sphere, no matter the lumpy surface actual shape. Bottom line: the shape of surface doesn't matter because field weakens as 1 by r squares and exactly cancels patch area growing by as r square for every direction. So the total flux only depends on how many directions are covered, which is always 4 pi fixed for any closed surface, not on the specific shape. So if we have a potato shaped closed surface, right, एक अजीब सा उबड़ खाबड़ सा एक 3D patch, whatever, एक complete 3D potato skin, तो उसके अंदर भी जो भी चार्जेस है उसके अराउंड भी हम स्फेयर बना सकते हैं, राइट। तो जो स्फेयर से जो फील्ड लाइंस निकल रही है इवेंचुअली वही उस अजीब से सरफेस में भी निकलेगी। सो मुझे तो इतना ही समझ आया। एनीवेज, question number 4 is why 2EA? We only wanted E at one distance R. Why involve both sides? This is about how Gauss law forces you to pick a specific closed surface, and the pillbox naturally has two relevant surfaces. The key constraint: the Gaussian surface must be closed. Remember, Gauss law only works with closed surfaces. तो उसे मतलब उसको पूरा complete लाइक फील्ड लाइन से बाहर लेने की क्या ज़रूरत थी? उसको फील्ड लाइन के ऊपर भी तो रख सकते हैं। दिस इज़ लाइक द फील्ड लाइन, देन इसके ऊपर भी तो सिलेंडर आ सकता था इंस्टेड ऑफ कम्प्लीटली क्रॉसिंग इट। तब भी एक कंडीशन फुल मतलब जो भी होता है फुलफिलमेंट, तब भी ये पूरी हो जाती। द क्वेश्चन सरफेस मस्ट बी क्लोज। रिमेंबर, गॉस लॉ ओनली वर्क्स विद क्लोज्ड surfaces fully sealed like a balloon. You can't just use one flat disk floating at distance r. You can't just use one flat disk floating a distance r from the sheet that's an open surface. Gauss law doesn't directly apply to it. Okay. Why a cylinder specifically and why symmetric? To use Gauss law, you need a closed shape where the flux calculation is easy, meaning E is either fully parallel or fully perpendicular to each part of the surface, as we discussed for an infinite sheet. The natural symmetric choice is cylinder pillbox that pieces straight through the sheet with one flat end at distance r on one side, and to keep the cylinder closed and symmetric, the other flat end at distance r on the other side. Real life picture: imagine pushing a soup can straight through a flat sheet of paper. So the paper cuts through the can's middle with equal amount of cans sticking out on both sides. That's pillbox. Could you make the cylinder asymmetric? Example: one end very close and one end very far. Yes, actually, go slow would still work, and you'd still correctly get this on each end through the algebra. Actually, we are trying to enclose the charge. Maybe that is why. Anyway, so on each side through the algebra, it's slightly messier since you'd need to handle two different field values E1 and E2 and use the known fact that both sides have equal field magnitude by symmetry. You and use the known fact that both sides have equal field magnitude by symmetry, but choosing it symmetric makes the algebra clean and simple, which is why textbooks always presented this way, not because physics forces it, but because it's smart and simple choice. Why does this tell us E at distance r? Since the sheet is infinite and field's magnitude is same at every point that same distance from the sheet, finding E at distance r on one specific end of pillbox is finding the field at distance r the other end just on the opposite side gives the exact same E value by symmetry. We are not just finding two different answers, we are using both sides together or bookkeeping to correctly apply Gauss law, which needs a closed surface, and by symmetry both confirms the same single value of E. Question 5: how can field strength stay same regardless of distance? Doesn't field go as 1 upon r square? This is fantastic and very important question. The answer is the 1 upon r square rule applies to a point charge, not to every charge distribution. Why point charge follows 1 by r square? For a single point charge, all the source is concentrated at one tiny spot. As you move away, the same total field line spread out over a bigger and bigger sphere area is 4 pi r square. So the density of the field lines, which is E, measures
thin out as 1 upon r square. Real life picture: a single light bulb in a room. Light spreads out in a growing sphere, getting dimmer the farther you stand. Why an infinite sheet is in completely different. An infinite sheet isn't single point, it's charge spread over an infinite flat area. Here's the key insight: as you move farther from an infinite sheet, you're not just moving away from one source point, you're also gaining a wider view of the infinite sheet and more of the sheet charge. From farther and farther away, sideways, start contributing field lines towards you too, as increasingly gazing or sideways angles. At increasingly gazing sideways angles. Real life picture: imagine you are floating above infinite glowing floor, not single light bulb, but the entire floor glows. Move higher up, you're farther from the nearest point on the floor directly below you. So the nearest bit contributes less, but you can now also see and receive light from much wider stretch of the floor. But light तो हर डायरेक्शन में ट्रेवल कर रही होगी ना, ये फील्ड लाइंस तो बस सीधा जा रही हैं, so I don't know. They receive light from much wider stretch of the floor, extending out sideways in every direction. Why extending out sideways? Which you couldn't see contributing before. This extra contribution from more of the infinite floor exactly compensates for being farther from the nearest patch. For a genuinely infinite sheet, this compensation is perfect and exact. The fall off from moving away cancels the gaining more of infinite sheets contribution effect, leaving the field constant with distance. And this is done. Mathematically, this is exactly our Gauss law's derivation. No R anywhere. The pillbox method automatically captures the whole infinite sheet contribution effect. The answer simply doesn't depend on R. It's not a mistake or approximation. It's genuine and exact physical behavior. Real sheets are never truly infinite. Of course, this is an idealization, but works well as long as you are much closer to the sheet than the sheet's actual physical size, that the sheet looks infinite from where you are standing. So, whatever, the topic is complete and we are done.